Funding for this program was provided by the Annenberg CPB project.
In 1820, Hans Christian Ørsted made his great discovery of how to turn electricity into magnetism. And at that point, every scientist in Europe knew that there was another great discovery waiting to be made, and that was how to use magnetism to create electricity. And they also knew that whoever made that discovery would become immortal. And so all of them scurried back to their laboratories and went to work. And then 12 years passed and nothing happened. Now, 12 years is a long time. For most of you, 12 years is 2/3 of your lives. It's nearly half of my life. And yet, in all that time, the discovery was not made. Now, in science, once you understand something, it's very difficult to remember what it's like not to have understood it. The fact is that during that period, many experiments were done that had the discovery in them in complicated ways that couldn't be understood. But once the discovery was made and reduced to the essence, it's just as simple as it can possibly be. Let me show you what it was. Here I have a simple loop of wire. My job is to make an electric current run around in this loop. The loop is connected to a galvanometer whose output is that point of light on the screen. So if I succeed in making the current run through the loop, that light will move back and forth on the screen. How am I going to make it work? Well, I've got to do it using magnetism. So here I have a bar magnet. To use this bar magnet to make a current run around in this loop is very easy. All I have to do is to move the loop into the magnet, or for that matter, back out again. That was it. That was the great discovery. Oh, yes, and incidentally, one thing more. If I move the loop back and forth like that, then the current runs back and forth and keeps on going. Well, virtually all electric power, one way or another, is generated by that mechanism. In other words, that discovery is the very basis of our electrical civilization. And that's our subject for today.
Without energy, civilizations go nowhere, not even in circles. But with a strong and steady wind and a comparatively simple machine, an endless supply of power can flow just about anywhere, and once it's been converted to electricity, accomplish what the ancients probably never even imagined. These days, it looks easy enough on the surface, but to understand how wind makes electricity, it's necessary to dig a little deeper and to come up with a bit of historical perspective. The Dutch were masters when it came to windmills. Holland had more water and less cultivated land than she needed. So necessity became the mother of invention, and the Dutch became very good at using the windmill to turn the Rhine River Delta into good dry farmland. But by the 1800s, another kind of revolution was in the air. And it was the churning power and glory of steam. For all their majesty, the future belonged not to windmills, but to steam engines fired by the mineral solid called coal. Coal was inexpensive, as steady as a rock, and as convenient as the closest railroad track. So for a while there, coal was really cooking. However, in commerce and chemistry alike, few things have ever remained the same for long. And even as coal was gathering steam in the industrialized nations, a new and different element entered the picture. It was called electricity. Nowhere was it more hotly pursued than at the Royal Institution in London. And no one had pursued it more closely than the 18th century's most diligent and intuitive scientist, Michael Faraday. He probed the mysteries of science because, for him, the building blocks of nature had been created with a fundamental unity. And Mr. Faraday believed that the blueprint was to be found within the laws of physics. With that belief, Faraday was motivated to unearth a new link between two of Mother Nature's fundamental forces, magnetism and electricity. His quest began in 1821 with Hans Christian Ørsted's discovery that the flow of an electric current creates a magnetic field. First, Faraday reproduced the experiment, and then, in a roundabout way, he took a major step forward. He invented a device that kept twisting as it followed the circular magnetic field created by a current. And from this point onward, when people thought of things turning to create power, they no longer thought of windmills and steam engines alone. With this amazing device, an electric current could create physical work. In other words, this was the world's first electric motor. But Faraday's restless mind saw more than circles of magnetic force in Ørsted's discovery. He saw a crucial scientific question. If an electric current could create a magnetic field, could a magnetic field create an electric current? The answer didn't come easily. It took lamp oil and paper, brilliance and tenacity, untold combinations of coils, magnets, and wires. It took more than a decade, which is why biographers note his legendary patience. But in 1831, Michael Faraday had the answer. As he connected a battery to one coil, current flowed briefly in another coil. He'd found the answer, and in the process he'd discovered the principle of electromagnetic induction. How does electromagnetic induction really work? In other words, how can a magnetic field drive an electric current around a circuit? Magnetic fields apply forces to electric charges, but only if the charges are in motion. The direction of the force is perpendicular to the velocity and the field, and depends on the sign of the charge, in this case, negative. For example, the charges might be electrons in a piece of wire. Just moving a wire through a magnetic field makes a current try to flow. But the field of a bar magnet can be perpendicular at every point to a circular loop of wire. So, moving the loop creates a force that drives a current all the way around the loop. The current flows one way if the loop moves upward, and the other way if the loop moves downward. Of course, a current also flows if the loop stands still and the magnet moves. One way if the magnet moves downward. The other if the magnet moves upward. In fact, Faraday found that any method of changing the magnetic field through a circuit would make a current flow. For example, he could induce a current by moving a bar magnet relative to a coil. And when Faraday connected a coil to a battery, the sudden increase in the magnetic field induced a surge of current in another coil. Both these ideas can be expressed in terms of magnetic flux.
The total magnetic flux through a surface is the integral of the component of magnetic field perpendicular to each bit of area that makes up the surface. As a loop of wire moves through the field of a bar magnet, the flux through the loop keeps changing. The changing flux causes a current to flow as if it were driven by a voltage. That voltage, called the electromotive force, E, is equal to minus the rate of change of magnetic flux through the loop. That's called Faraday's Law of Electromagnetic Induction.
A generation later, and a continent away, other pioneering geniuses would make the most of Faraday's discovery. Their names were Thomas Edison and Nikola Tesla. Unlike Faraday, however, their primary ambition was to make machines work and to make them pay for themselves. Edison saw a lot of profit in the business of electricity. But if he were to realize it, he'd need to light up the city of New York. That would require a network of very powerful generators. And no matter the engineering shape they'd take, the principle of every dynamo would come from Faraday's law of electromagnetic induction.
Rotating a loop of wire in a constant magnetic field continually changes the flux through the loop. The resulting voltage and current are sinusoidal, going first one way, then the other.
Using elaborate sliding contacts attached to the rotating coils, Edison was able to compensate for the oscillating voltage, drawing current that always ran in the same direction from his generators. Tesla thought Edison's system of direct current was costly and inefficient, and that alternating current would do the job better. But AC or DC, one question remains: which way does the induced current flow?
Current flows through a coil of wire whenever the magnetic flux through it is changing. The current flows one way if the flux decreases, and the other way when the flux increases. But the current induced in the wire also creates a flux of its own, whose direction depends on the direction of the current. The flux created by the induced current always opposes the change in the external flux. This rule is known as Lanzas Law. The net result of both fields added together is to slow down the rate at which the magnetic flux through any circuit is able to change.
As electric power grew more important, Lanzas Law didn't slow down the rate of change of technological progress. And steam engines weren't out of the picture, not by a long shot. Engines fired by both coal and oil continued to turn generators and create the power of electricity. However, the more that coal and oil were taken away and used up, the more obvious it became that the Earth began with a limited amount. And for some, when it came to fossil fuels, the end was already in sight. So the search for alternatives continued. For a time, hydroelectric power flowed with promise. But in the search for a clean, efficient, and abundant source of energy, all the world's rivers together would never provide enough. And by itself, neither would the wind. But along with geothermal and solar power, the wind provides cheap, decentralized energy that can share the load with traditional centralized generating plants. Taking advantage of current technology, these windmills are much more efficient than their Dutch counterparts of a few centuries ago. In any case, whether electric power comes from the wind or the water, from nuclear power or from coal, it's generated using the principle of electromagnetic induction. And the same principle plays a role in any circuit where electricity is used. An electric current in any circuit creates a magnetic field which, whenever it changes, induces a current in the same circuit that opposes the change. This phenomenon is called self-induction. The effect of self-induction is larger in a coil of many turns, called a solenoid, precisely because it loops many times around the changing flux. That's why a solenoid is used as a symbol of self-inductance in an electric circuit, where an inductor may be an element like a resistor or capacitor.
Current increasing in an inductor causes an opposing electromotive force, according to Faraday's law. And since the flux is proportional to the current that creates it, that electromotive force is equal to minus a constant L times the rate of change of current. L is called the inductance of the circuit element. An inductor opposes and slows down the buildup of current in a circuit, while a resistor may cause the current to decay by dissipating energy.
But beyond such practical concerns, what's the value of Michael Faraday's theory? For starters, unlike a motor, it's not simple and obvious. And unlike any machine, it's not something one can put a price on. In fact, the value of electromagnetic induction is beyond the economics of technology. And that's because Faraday's theory reveals something new about the nature of electric and magnetic fields, and in the process changes the rules by which nature's game is played. Magnetic fields circulate, but never converge to a point. Electric fields converge to a point, but never circulate. In mathematical language, that means the line integral of an electrostatic field around any closed path is always equal to 0. But when the magnetic flux through a loop changes with time, it creates an electromotive force around the loop. And that electromotive force is due to an electric field whose line integral is not equal to 0. In other words, there is a way to make electric fields circulate after all, and it's accomplished by changing the magnetic flux. When Faraday discovered that a changing magnetic flux could make an electric field circulate, he added something extraordinary to the laws of electricity and magnetism. So, while it's often said that there's nothing new under the sun, the saying doesn't apply to electromagnetic induction.
Now I'd like to show you something truly extraordinary. But first, I have to explain to you what it is you're going to see. When we first started discussing electromagnetic induction, this is how I explained to you how it would work. I said the wire moves through the magnetic field, and because of the motion of the wire, the charges inside have a force on them, and that sets the current into motion. But when we finally formulated Faraday's law, we were describing it in quite a different way. Then we said that the electromotive force is proportional to the rate of change of the total magnetic flux through the circuit. That suggests that the experiment could be done in quite a different way. What we could do is have a solenoid, that is a helical winding like this, in which the wire goes around and around, and if we pass a current through that, it creates a magnetic field in this direction. Now, if I have a loop of wire around this solenoid like that, and connect it to a galvanometer like that, then when I turn the solenoid on, the flux through that loop will increase even though there's never any magnetic field at the position of the wire at all. And according to Faraday's law, the galvanometer should jump. Well, of course, you'll object to that. You'll say the magnetic field at the position of the wire is not really 0, because the magnetic flux that goes through the solenoid really does have to return outside somewhere, and so there's some magnetic field outside. But I can cure that problem by taking the solenoid and making it bend around onto itself into a kind of a donut, or toroid. Here's what the toroid looks like, and it has some windings of metal wire around it, and when a current is passed through those windings, lines of magnetic flux go around through the toroid and close on themselves without ever going outside. So the magnetic flux outside of a toroid is really equal to 0. Now, if I took a loop of wire and ran it through the middle of the donut and then back around and closed it on a galvanometer, when I turn on the toroid, the galvanometer should jump even though the magnetic field at the position of the wire is exactly 0. That's what I would like to show you. I have here a toroid. I can turn the toroid on by means of this switch here, and when I turn it on, there'll be magnetic flux inside, but there won't be any magnetic field at all outside. And I can show you that because I still have my loop of wire here connected to the galvanometer. Now, you know if there's a magnetic field turned on at the position of this loop of wire, the galvanometer will jump. So I can put the wire right on top of the toroid like that, as close as I'd like to get it. I turn it on with this switch, and you can see that nothing happens. The galvanometer doesn't budge. Nothing. When I open the switch or close the switch, absolutely nothing happens. But if I take this wire instead and put it through the donut, the result is completely different. And I can do that just by opening the wire, threading it through the middle of the donut like this, and closing it again. Now, even though there is still no magnetic field at the position of the wire, when I turn the toroid on, the galvanometer will jump. Ready for this? Watch. There it is. And when I turn it off, the same thing will happen again, like that. Now, that is the essence of electromagnetic induction. Now, there's something else over here that I wanted to show you about electromagnetic induction. It's this pendulum. This is an ordinary pendulum, but it has a piece of copper at the end. And when it swings, the piece of copper swings between the poles of an electromagnet. But the magnet is not turned on right now. If the magnet were turned on, imagine what would happen. The piece of copper would swing into the magnetic field. Because it's swinging into the magnetic field, then by electromagnetic induction, electric currents would be induced to run around in the copper. Now, whenever currents run around in a piece of metal, that causes heating. And so there would be heating, and that means that energy is being lost from somewhere. But where does the energy come from? Well, the only place it can come from is the swinging of the pendulum. So the pendulum should actually slow down if I turn on the magnet, which I can do by closing this switch. So here's what I'll do. I'll get the pendulum swinging again, and you sort of get the rhythm of the pendulum swinging back and forth. And then when I close the switch, you'll actually be able to detect that the pendulum slowed down. Okay, so here we go. I'll get it swinging again. Watch it. I'm going to close the switch right now. Watch this. There. Did you notice that? One more thing I'd like to show you, and that is that not only can electromagnetic induction stop a piece of metal, it can get one going again. Because a piece of metal doesn't like to be in a region of strong changing magnetic field, which I have right here. If I take this ring of aluminum and put it down in the field and turn it on, you should actually be able to see the aluminum jump when I turn the field on. You ready for this? Here goes. Watch. There. Well, I can't do any better than that, so I'll see you next time.
Funding for this program was provided by the Annenberg CPB project.
You can order these programs on videocassette. Call 1-800-LEARNER and visit us at www.learner.org/channel, the Annenberg CPB channel.